Okay, we'll get started. So, as promised, today the topic of discussion is generative AI and specifically reinforcement learning with human feedback. I'm not going to talk about the theory of generative AI because that's a class in itself, and hopefully, I'll get to teach that class at some point of time in the future. But this is not the time. So today the main topic is reinforcement learning with human feedback. And of course, this is the last lecture in reinforcement learning. So I want to kind of give you the train of thought as to where this topic comes from, what all things have we done, and where this topic of reinforcement learning with human feedback comes from. So we have the typical, we have the state space, action space, state dependent action set, the reward or cost function, the uh, the state transition function, and then the noise distribution. Anything am I missing? I think I'm missing the discount factor. Uh, Today I'll assume that the discount factor is, well, in some cases there'll be discount factor, in other cases we'll use the total cost criterion. So for finite horizon, so the things are going to be slightly, the settings are going to be slightly different. Let's assume for the time being that the state action and state dependent action sets. So state dependent action sets for today, just assume that it's the entire A, although I believe that the results can be extended to the setting where you have state dependent action sets. So what did we do in the majority of this class? So we looked at a cost function. Let me use the reward function for today. So I look at R and F. I give it an input to a value iteration algorithm or a policy iteration algorithm. I get V star or Q star, and that allows me to compute mu star, which is the optimal policy. Right. So this is what we have discussed for a majority of the class. We talked about value iteration algorithms, policy iteration, lambda policy iteration, enhanced policy iteration, and how do you use the reward function and the state transition function in order to compute V star and Q star and mu star. Even for the general state setting, this can be done as long as you can store the V star and Q star in your memory. And then we talked about fitted value iteration, where you have R and F. You use fitted value iteration or fitted Q value iteration, and you get V hat, Q hat, and from there you can get mu hat. And as long as the inherent Bellman error is small, you can be assured that mu hat will be close to mu star, or at least the value of mu hat is going to be close to the value of mu star. Then we said, okay, I don't have this reward function and the state transition function. I have a simulator. I have a simulator, or I have a real world system from which I can generate the data for every policy. And then we talked about empirical fitted value iteration, empirical fitted Q iteration. And I said that, well, we can get F hat and G hat, which is roughly close to V star and Q star with high probability. And from there you can get mu hat, which is hopefully close to mu star, supposing you have sufficiently large number of samples. Within this topic, we talked about experience replay. We talked about n-step, multi-step rollout. We talked about reward shaping. And we talked about some intelligent sampling methods. So these methods try to reduce the sample complexity, improves the convergence speed, and so on. So we talked about some of these stuff that allows you to compute f hat and g hat using as few samples as possible. Right? So that was the topic of discussion in the previous class. Now there are other important problems within reinforcement learning. So let me talk about that. I have f and I have mu star. I'm going to talk about inverse reinforcement learning today. Inverse reinforcement learning that gives me the reward function R that generates the policy mu star. Okay, so this is reinforcement learning where you give it the data set and you get the value function. The inverse RL is you give it a policy and the state transition function, and it gives you the reward function. That's inverse reinforcement learning. This topic was studied by Andrew Ng and Russell in 2000. The name of the paper is Algorithms for Inverse Reinforcement Learning. So that's the paper we'll be talking about today. It's not going to take too much time. It's a very simple and straightforward problem. Okay, so that's inverse RL. And then the second part is I know f, which is the state transition function, and I know preferences over SA trajectory. So this is the data set I have, the preferences. I'm going to map it to this technique called reinforcement learning with human feedback. I'm going to get R phi of SA, which is the reward function parameterized by a vector phi. And then from R phi, you can apply PPO or GRPO. So PPO algorithm is something we have already talked about. GRPO is something we'll talk about today. And then you get mu star, which is the optimal policy. Yes. We'll talk about it. So, but preferences generally means that let's say you have a robot and you want the robot to go from here to there. And in one case, the robot went from here to there in straight line. In the other case, it went all over the place in the class and then it went there. So definitely you would say that I prefer this trajectory over the other trajectory which went all over the place in order to get there, right? So that's called the preferences. I prefer this trajectory over that trajectory. Okay. So the trajectory is the state action trajectory. So S0, A0, S1, A1, S2, A2, S3, A3, all the way up to S capital T, A capital T, assuming that you're looking at a capital T horizon decision problem. Okay, so this is the topic that we'll be talking about today. So there are three topics to study today. One is inverse RL, one is reinforcement learning for human feedback. So what happens in this particular block? And then PPO algorithm is something we talked about. GRPO algorithm is kind of a new algorithm in the RLHF world. So we'll talk about GRPO. So these are the three topics that are subject of discussion today. Any questions so far? Okay. So let's talk about the inverse reinforcement learning. Actually, this one is simple. So let me just write it down here. This is Andrew Ng was a co-founder of Coursera. He's a faculty at Stanford. He's also co-founder of Coursera, and he's involved in a lot of startups. So Stuart Russell was a very big reinforcement learning guy in Berkeley, and when Andrew Ng wrote this paper, he was actually at Berkeley doing his PhD back in 2000. Okay, so what is V mu? We have studied in the past okay, here I am going to make a small simplifying assumption. The reward function is a function from state to real line. So instead of it being a function of state and action pair, it's a function of just the state. It's not that you cannot assume a more general reward, but it's just that the algorithm will be way complicated. So I'm just trying to do the simpler one, which is what is presented in this paper. This paper has probably like 7,000 citations or so. So I'm pretty sure you will find more recent papers on this topic that that solves this. So here the state space is finite, and P is the state transition function. So P mu is equal to I prime given I is this is summation over all u. So now you can view P mu as a matrix. You can view P mu as a matrix. So this is something we have done somewhat long time back, I think in October. So you may not remember, but this is the expression for the value function, which can be given by this, and therefore I can write it as identity minus alpha P mu inverse R. Okay, so if you go back to our derivation of the PPO algorithm, that's when we talked about this particular way of representing the value function. Okay, now the problem is I don't know the reward function. I know the state transition function. I know mu star, right? Those are the two things I know. I know the state transition function and I know mu star. I want to be able to find R such that V mu star, so I want V mu star is greater than equal to V mu for all mu. I know this. So given V mu star is greater than equal to V mu for all mu, find R. That's the question that we need to solve. How do you think you would solve this question? So I know that this policy is optimal. I look at you driving. I'm sure whatever your driving strategy is the best driving strategy for you, but neither you nor I can write out a reward function that explains your driving strategy. Okay, you are a robot operator. I can collect data about your policy. I can figure out what your policy for running that robot is, but I don't quite know what the reward function is under which you are actually operating. So I need to find out the reward function. The good thing is if I can figure out what your reward function is, I can embed that reward function in my new robot that I'm creating, and then I can run dynamic programming algorithm in order to find the policy for that particular robot under different settings. So I see how you are driving in Ohio. I want to drive in Alaska. I want to be able to get your reward function, and then I will port that reward function in my Alaskan autonomous car, and then I can drive in Alaska without any problem, because the reward function embeds the information about how you view good policy versus bad policy. So how would you solve this problem if this is what you want to do? So remember that mu star is optimal for V mu star as the value function, right? So in particular, for any non-optimal policy, if I apply the one-step rollout, then what I mean to say is R, so R plus alpha P mu times V mu star is less than equal to R plus alpha P mu star V mu star. So mu star is the optimal policy. P mu star is the transition kernel under the optimal policy. So if I pick some other policy mu, I will get a total reward that is lower than the reward I was getting under the policy mu star. That's just the basic optimization. And the reason why this is the case is this is max over u of R plus alpha V I prime expectation. This reward is just a function of I. Okay, let me maybe write it down properly. So I have Ri plus alpha P mu star V mu star evaluated at I equals to max of u Ri plus alpha summation over I prime So this one is supposed to satisfy this particular expression, maximum over all action of the current reward plus future value with a discount factor. Remember that reward here is purely a function of state. It doesn't take into account the action. Right? So this implies this particular inequality. Any questions so far? I want to make sure that before I proceed further, I want to make sure that you all agree that this inequality is true, because this is the core inequality that allows us to define the reward function. So this is the best policy, and this is the best value function. And if I pick some other policy, then I'll get a reward, total reward, which is less than equal to the reward I'm getting from the best policy. Okay. So how do I find the reward function from here? This is true for all mu. Okay, I'm going to erase this part. So this implies that alpha P mu star minus P mu V mu star is greater than equal to 0 for all mu. This is a vector, this is a matrix. So I'm multiplying a matrix by a vector, I get a vector. Each element of that vector is non-negative. I'm going to substitute this expression, and this alpha is just a positive term. It's a scalar positive number. I can just move it on this side and I can make it 0. So what I get is P mu star minus P mu I minus alpha P mu star inverse R reward is greater than 0 for all mu. Okay. So this is so basically what here. So P mu star is something you know, because you know mu star, and you know the state transition function. So you know P mu star. You can construct for every policy mu, you can construct this matrix P mu, You can take the difference. This matrix is fixed, so I can just compute this once and I'm done with it. This is a matrix, I know about it. Alpha is the discount factor, I know. I is the identity matrix. I can just do the subtraction, invert it, keep it in my memory. Now I need to find a vector R, which is a S dimensional vector which satisfies this inequality for every mu, right? So you can set it up like a linear programming problem with this as a constraint, and then you can solve for the reward function. You can have like minimum of the R infinity norm. So you want to minimize either R square or like the L2 norm of R or L1 norm of R or L infinity norm of R, it doesn't matter. Subject to these constraints for all mu, you get a linear program, you can solve the linear program and you're done with the finding the R for which mu star is the optimal policy. So that's what the idea of inverse reinforcement learning is. Now, if you have data and stuff, you can then do an appropriate data version of this, some of which has been talked about in that paper, Eng and Russell. And then there are 7,000 citations, so I'm pretty sure many people have talked about what the data-driven version of this idea is. So that is the topic of inverse reinforcement learning. So if I know the policy and if I know the state transition function, what's the reward function that explains the optimality of that particular policy? So I can look at your driving data, driving strategy. I know the dynamics of your vehicle, and I can figure out what's the reward function under which you are operating your vehicle. Yes?
So given these algorithms, the estimated reward function should be a stat.
Technically, you don't have a unique reward function that gives you that policy, because you can scale the reward function by any positive number and that still satisfies the
But like with some normalization scale.
Exactly. So that's why I said you do the minimization of the L2 norm of the reward function subject to those inequalities.
So the solution will still be a stat.
No, if you're minimizing the L2 norm, then you will get, I mean, technically speaking, you might have a set, but it could be a unique solution also, because you are minimizing a squared norm of the reward function. Okay. Then it's a strictly convex problem with subject to linear inequalities. So you probably will have a unique solution. Any other question? Okay. Certainly the reward is non-unique. I can replace this R with any positive multiple of R. Like replace this R with 500 times R, and that still satisfies this inequality. So therefore you don't, it's a set of reward functions. And then you can find the optimal, you can come up with some objective function in order to get a unique reward function that solves this problem. Okay. Any questions so far? No other questions? Awesome. Now we have a new setting. I have a large language model. I have a robot that I have 20 graduate students. Each of the graduate students have trained the robot to do something, and I want to find what's the best policy. And the problem is I don't have a reward function. I know if the robot is doing well. I know if the robot is not doing well, but I cannot really write out a reward function for every different problems that the robot is solving. So then the question is, I have a preference, and I need to convert that preferences into a reward function so that I can encode that reward function into the robot and then forget about the preferences forever. Right? So that's the question that is studied under the umbrella of reinforcement learning with human feedback. The fact that you want preferences to get mapped to a function, it's a fairly old topic. It was studied back in 1928 by von Neumann and Morgenstern. maybe von Neumann in 1928, and then they wrote a book, Theory of Games and Economic Behavior, which was the first book on game theory back in 1944. And the idea there was I have preferences over my actions. So there was no state, there was no dynamics there. So I'm going back to 1944. They are looking at people who are buying and trading and making some actions in the market, and then they want to figure out, if you have preferences over the actions, can I come up with a function of the action that explains those preferences? And that was known as utility theory. Okay, I'm not sure how many of you have learned about utility theory, but that was studied under the umbrella of economics. No dynamics, no state, just action. Can I map action to a reward function? And so he came up with what is known as axiomatic decision theory. So he came up with a bunch of axioms that the preferences should satisfy. And if those axioms are satisfied, then there is a reward function as a function of action. So that's something that von Neumann and Morgenstern studied back in 1944 in the first book in game theory. Fast forward to 1952, we had a bunch of agriculture scientists, and their name was Bradley and Terry, which is the model that people in large language models are using. So Bradley and Terry were looking at a very unique problem. So the problem was they had pigs. They wanted to feed pigs some sort of diet, and they wanted to figure out which pig is going to taste better once it gets cooked. Okay. but the tasting better part is a human feedback. So a human will taste the meat and will tell you whether or not it is tasting better than the other. But the feed is something, whatever you are feeding the pig is something that you have to decide early on. So they were doing this research, and they came up with a way to mapping the preferences of taste with the reward function of the food that you are feeding the pig. Okay, that was their problem. I am pretty sure that they weren't looking at the game theory literature. Okay, they were just looking at, I have this statistical problem. I need to figure out what is the food that I'm supposed to be feeding this pig, and I need to be able to come up with a reward function for that particular food. So that was a Bradley-Terry model. So they came up with some model for figuring out the preferences, how to go from preferences over taste to the reward function of the feed. And they came up with this Bradley-Terry model. And I'll talk about Bradley-Terry model in a bit in the context of reinforcement learning. I don't want to go into their specific problem. Then there was a book written, Individual Choice Behavior. This book was by Luce, first published in 1959, and then it was republished in 2005. And that is the book that many people cite in the reinforcement learning RLHF literature. So something you should know about. The book is called Individual Choice Behavior. So it contains a lot of information on how do preferences over set gets converted into a reward function. What are the statistical models to do that? So the existence was proved by people in economics, von Neumann and Morgenstern. But the actual computation, so they didn't have the computation, they didn't have the statistical part. The statistical part was something that was studied by people in economics and decision theory later on, and that's the book Individual Choice Behavior by Luce in 1959/2005. Okay, so now let's talk about this core idea of reinforcement learning with human feedback. So we know about the existence, we know about the statistical model. Now, how do we use that in the context of reinforcement learning? So let me first introduce what happens in a large, like what's the RL problem in the large language model, what's the RL problem in the diffusion model, and then I'll get into the Bradley-Terry model for doing RLHF. So Bradley-Terry model converts this into the reward function. And then I'll talk about GRPO. large language models. So I have S naught is my prompt. The state space is token space raised to context length. Just to give you an idea, each token is a vector in R, let's say 1000. I'm just giving you a rough idea. This is from GPT-5. I have found it on Google, so I'm not sure whether I should trust it or not trust it, but it just gives you an idea. It doesn't have to be precise, but it gives you an idea. Context length is 272,000, and there are the number of tokens is equal to 100K. So it kind of gives you an idea of what the state space looks like. Okay, so each token is represented by a 1000-dimensional vector. We have 100,000 such tokens, so the token space is 100,000 1000-dimensional vector, and then the context length is 272K. So this goes in the exponent. The context length goes into the exponent of the state space. So that's the state space. The action 80 is the next token. The state update expression is the policy here, mu theta, is a transformer model. And this takes as input ST and gives an output, the probability distribution over all the tokens. So the transformer model takes as input ST and outputs the probability distribution over all the tokens. That's the policy mu theta. This is a finite horizon problem. So let me write down the horizon length. Capital T is 128K. This is finite horizon. But the horizon length is very high. Any questions on this? You know what is this truncation operator? So if AT and ST becomes larger than the context length, if it is greater than 272K, then you remove the bottom part of the ST so that the context length is always 272. So this particular vector, this ST plus 1, should always be 272K. It should have a total 272K tokens. So if you have more tokens than that, you sort of have to truncate, remove all the old tokens so that you can keep pushing new tokens in. That's just the truncation operator. Any question? Okay. So this is the policy, which is a transformer model. You look at the current set of tokens, and then you try to decide what's the next token that needs to be generated. In order to train the first policy, you look at Wikipedia, you convert the Wikipedia pages into a bunch of tokens, and then you try to do the next token prediction problem. It's just a regression problem. There is nothing much going on there. You look at Wikipedia and then you just train this particular mu theta. Now the problem is you give it a question. So S naught is the query, S naught is the prompt. I want the recipe for a bread, or I want to figure out how to fix my car, or I want to do whatever X, Y, Z. That's the prompt. And then the mu theta starts generating a whole bunch of responses. And some responses are correct, some responses are incorrect, some responses follow the grammatical uh, uh, syntax of the English language, some tokens will not. And so now that you have trained this bad policy, the first bad policy, now you want to improve upon that bad policy, right? Now, if I look at a paragraph, if I look at a paper, I know it's a good paper or a bad paper, right? But I can't really say, it's very difficult for me to come up with a reward function so that I can get a better policy. I can come up with a better transformer model, right? So I look at the output from this transformer model for every prompt and for every chain of prompt. And I look at the output and I tell you whether this output is better than that output. That's pretty much all I can say. But I can't really come up with a reward function. So the question that people at OpenAI asked back in 2017 is, how do I know what's a good answer and what's a bad answer? How do I train the transformer model to come up with good answers and not come up with bad answers? Okay, so that's the problem in the large language models. Now let's talk about the diffusion model. So the diffusion model is also, so I have a context. Let me call C. C is already used as a cost. Okay. So let me say S naught is a Gaussian vector and a context. So this context is the same as prompt. So you can think of it as prompt. Maybe I should not write it as context. I should write it as prompt. Okay. I'm going to write something which might not look good. Okay, let me write it anyways. So my AT is equal to mu t st, and this is given by this is learned from data. And in most cases, this AT and BT are scalar values, but I'm writing it in the matrix format because I want to be dimensionally consistent. The only bad part here is that S0, we only take the Gaussian vector, not the prompt. The prompt is basically used only in this particular definition of the mean of the Gaussian vector and the covariance of the Gaussian vector. But otherwise, this particular thing is just looking at the Gaussian vector. This matrix update is just the Gaussian vector. And then ST plus 1 equals to AT. Wonderful. And then I have so this particular learning algorithm comes from the paper called DDPM, Ho et al. 2020. And let me tell you the name of the paper. Denoising diffusion probabilistic model. That's this paper. Denoising diffusion probabilistic model came out in 2020, and it tells you exactly how do you learn this M and this sigma from data. And it also tells you what this scalar. I mean, I'm again saying that it's a diagonal vector with all elements along that diagonal is the same. So it's essentially scalar times identity, but I still want to keep it in matrix format so that I'm dimensionally consistent. So this matrix, this training, all of that is given in this particular paper by Ho et al. In 2020. Denoising diffusion probabilistic model. That's the paper name. Okay. So now the question is, okay, so do you guys know where diffusion model is being used right now? It's being used for image generation. It's being used for video generation. It's being used for music generation. So this is just a language model. It just generates the text. This one generates all the other forms of multimedia. That's this algorithm. So that's where, so broadly that is studied under the umbrella of diffusion model. So this one is a language model, and this one generates all kinds of multimedia. Here also you have a time horizon capital T, and this is of the order of 1,000, or at least, in early papers it was of the order of 1,000. I don't know whether it has gone up to 100,000 or something now, but many of the research nowadays is not in public domain, so we wouldn't know what exactly the horizon length is at this point of time. Okay. So this one is, so I hope you understand what the MDP problem here is. So here I know what's a good answer and what's a bad answer. Here I know what's a good image and a bad image, or I know what's a good song or a bad song, or I know what's a good video or a bad video, right? So for instance, in the early days of diffusion model, you will sometimes see you put in a prompt, draw a human hand, and then the image, which is S capital T is the final image. And you look at the final image and you will have 7 fingers or 10 fingers. And you know that that's an unrealistic number of fingers on a human hand. So you would give that an input that, look, you can't have, like, it's a bad image of a hand because it has like 10 fingers or something like that. So you can give it some input. Once the final image gets created, you know whether it's a good image or a bad image. But you don't quite know what's the reward function that would generate the right image, what that reward function is going to look like. All right. So now let's go back to 2017, and the paper is Cristiano 2017, Yang et al. Sorry, these are all multiple authors paper. So this paper is for robotics application. So they were looking at the final control commands to the robot, and they were telling They were figuring out whether this set of sequence of control actions are actually leading to a desirable behavior or not. And later on, the same idea was applied to large language models. So even though they weren't looking at large language models in this paper, it was actually being created for large language models back in 2017. So these guys are from OpenAI. These guys are, they are all in China, but I think they are in Peking University, but I could be wrong. Okay. This was doing it for the diffusion model. So this paper is studying RLHF for diffusion model. This paper is studying RLHF for robotic/multimedia applications. The name of this paper is Deep Reinforcement Learning from Human Preferences. And the name of this particular paper is Using Human Feedback to Fine-Tune Diffusion Models Without Any Reward Model. Okay, so what's the problem statement? So I'm going to define sigma as S naught, A naught, S1, A1, S capital T, A capital T, or SK, AK, SK plus 1, AK plus 1, ST, AT. This is known as a trajectory. Bad policy mu theta. So I have this mu theta. This is my mu theta. This is my mu theta. So I have a bad policy. The bad policy is typically the first policy you get after doing the training using existing data sets. So you have a bad policy mu theta. You have generated this trajectory using this bad policy. So in the case of large language models, you start from the initial prompt. You kind of remove all this S1 and S2 and S3 because it contains the same information as ST and AT. But it doesn't matter. This is the trajectory, and this is the trajectory in the diffusion model. And the reason why this trajectory is picked in the diffusion model is because the first few steps are going to be pure Gaussian noise, addition of Gaussian noise. So it's just going to look noisy. But after a certain time step, maybe like 500 steps or 600 steps, it'll start looking like a human image or like a real image. And then you look at all the images that are being generated after that particular time step. So you ignore the first few time steps in the trajectory. So now that I have the trajectory, I can show this trajectory to a human being, a bunch of human beings, and they will tell me whether this looks good or bad. So whether this answer is good or bad, or whether this image is good or bad, or music is good or bad, or video is good or bad. So now I have collected this data set, sigma 1, sigma 2, y1, y2. So I have given two trajectories to the human being, and they need to rate which of these trajectories is better than the other trajectory. So y1 is equal to 1 if sigma 1 is better than sigma 2, 0 if sigma 1 is less than sigma 2, and 1/2 if sigma 1 is equal to sigma 2. So if you think that both trajectories look the same, they look reasonable, then you put is equal to half, and then y2 is of course 1 minus y1. So this is half. If in case sigma 2 is better, this trajectory looks better, sigma 1 looks bad, then y1 becomes 0, y2 becomes 1. And if sigma 1 is better, sigma 2 is bad. So sigma 1 is a good answer, sigma 2 is a bad answer. Then y1 is equal to 1, y2 equals to 0. Now here is the, so now what you have done is you have collected this data set. So we have collected this data set, sigma 1, sigma 2 I equals 1 to capital N. I've collected this data set from, do you know how they collect this data set? No? So there are many ways to collect the data set. So one way to collect the data set is if you look at the answers that is generated from OpenAI, there'll be a thumbs up or a thumbs down button. So thumbs up means this answer is good. So this becomes 1. If it is thumbs down, then this answer is bad, and you have sigma 2i, which is bad. So one way is thumbs up, thumbs down. The other way is you hire a bunch of people in Nigeria, Kenya, India, Indonesia, whatever, and you keep sending them all this data set getting generated by ChatGPT or whatever, and you let them rate whether it's a good output or a bad output. So that's another way to do it. Right? So there is multiple ways to collect this particular data set in a real world setting. Okay. Now the question is, I want to map this data set into a reward function of SA. So I have this data set S0, A0, S1, A1, ST, AT, SK, AK, SK plus 1, whatever, all this stuff. I want to map this data set that I have collected into a reward function. So what's the way to do it? So that was the original paper Cristiano that popularized that particular algorithm. So let's talk about that. Okay. Any questions so far? How are you guys doing? Okay. So this goes back to the Bradley-Terry model. Which is, you can think of it as an assumption. I mean, there is no truth to it, but it's just an assumption that if I had this hypothetical reward function R phi, and I have this trajectory preferences, then the probability that sigma 1 is preferred over sigma 2 is given by exponential summation SA in sigma. Let me put this brackets around this so we know that we are looking at pairs. So this is SA in sigma 1 R phi of S comma A over summation I equals 1 to 2 exponential of summation SA in sigma I R phi of SA. And then you construct the loss function as a function of phi, which is minus summation over the entire data set of y1 log log. There is a negative sign here, and this is a loss function as a function of phi, which is the parameter set for the reward function. Okay. So this is the core idea of reinforcement learning with human feedback. I came up with a pretty bad policy. The bad policy came from whatever. I did a supervised learning problem. I did some classification. I came up with some basic diffusion model and used the existing data set of Google Photos or YouTube videos or all the songs that people have ever written. And I created a bad policy, mu theta. I'm calling it a bad policy because I don't know whether it's going to generate good stuff or bad stuff. So I don't know what it's going to generate. So it's probably going to be sometimes good, sometimes bad. And I have some preferences. Sometimes the preferences could reflect uh, correct answer versus wrong answer. Sometimes the preferences could reflect um, the preferences of the diverse group of people who are interacting with the system. So let's say you've created a system for people who have mental health problems, right? So then the preferences would actually come from people who are interacting with that particular system, and so it won't be the same as preferences of the wider public, because wider public might be interested in something else, whereas people who are actually interacting with the system in order to get help will have a completely different preferences. So no matter what the set of people are, what your target audience is, you collect preferences from the target audience, and now you want to map it to the reward function. And so the Bradley Terry model is being used to generate a loss function that parameterizes the reward. Typically, it's a neural network. So it generates the loss function, and then you try to optimize uh, by picking an appropriate. I guess I should write it as a function of phi. So this probability is a function of phi because R is a function of phi. Now you have a loss function in terms of phi. You can minimize this loss function by using the typical gradient descent method, and you can design a reward function. Once you have the reward function and once you have a bad policy, how do you construct a good policy? You apply policy gradient method, right? We have learned about it in PPO algorithm that if you have a policy, you have a reward function, now you can apply PPO algorithm, which we talked about, in order to create a good policy using the policy gradient approach. Okay, so now let's come to 2024, and this is paper is Shao et al. And this is from DeepSeek. The title of the paper is DeepSeek Math, Pushing the Limits of Math Reasoning in Open Language Models. So they were interested in figuring out how to come up with a policy, mu theta, which gives you the correct reasoning on math problems. Okay, so we are all trying to solve math problems in our day-to-day life, and we want the reasoning to be correct. And whatever policy I have trained on Wikipedia and all that open, all the information available in the public domain, sometimes it gives me the right reasoning, and sometimes it gives me completely random reasoning, right? I'm not sure how many of you have tried to solve problems using chat GPT. Maybe that's the wrong question to ask here. uh, but uh, but nowadays I'm seeing a lot of assignments that are copied and pasted from chat GPT. So anyways, that's the world we are living in. So actually these are the culprit. These guys have the one who developed that system that people are now using to generate assignment solutions. But anyways, so that was the problem that they were studying. And the real problem that they had with PPO was, remember that in PPO you need to have a policy mu theta, and then you also need to keep track of the advantage function a as a function of theta. How many parameters are these guys using for policy, for their large language models and stuff? It's humongous, right? Typically it's of the order of 1.8 trillion parameters. So this theta is 1.8 trillion dimensional object. So if you have to approximate another advantage function with 1.8 trillion parameters, it becomes a headache, right, to keep track of that advantage function. And it's further compute, more memory, more GPU, more this, more that. They didn't want to go through with all that hassle. So they said, look, I have this reward function from the Bradley-Terry model. I was able to solve this loss function. I got a reward function. Now I have one model, one set of GPUs that's holding this policy mu theta, one set of GPUs that's holding this policy, this reward function R of phi. And now you are asking me to have another 1,000 GPUs, which is going to hold the advantage function, and that's just too much. Don't ask me for all that stuff. I don't have that much money. Okay. So they said, let's look at the PPO algorithm, and then try to modify the PPO algorithm in a way that's advantageous to us, and I don't have to keep track of the advantage function. So what's the PPO algorithm? In PPO algorithm, I'm trying to solve the following problem. I'm minimizing over theta of summation t equals 1 to capital T. I'm going to do the simple PPO. I'm not going to do the full-blown PPO that people are talking about. This is the advantage function. And this is also parameterized by some theta. I mean, not the same, it could be the same theta, it could be some other theta, but this one is also parameterized with some other vector. And this is the importance, this is same as the importance ratio that we had talked about, and you've done an assignment on that. So this is what the PPO algorithm is trying to solve. And then there is a minus beta dkl hat, because this is also estimated from data, pi theta old. So that's the PPO algorithm we had derived in the class and we had talked about. Okay, so here the most difficult part is to be able to compute this advantage function. Every time I update the policy theta, I need to compute this advantage function, and I need to then store or train a model for that particular advantage function. And I don't want to train that model because I'm already spending effort into pi theta, and I'm already spending effort into storing R phi. So I don't want to store the advantage function. So they came up with the following option. They said replace AT with let me give it in a bit with something else, with some other estimate using multiple outputs from pi theta old. So what is the idea here? So the idea is I'm going to generate for a given S naught, generate sigma 1 S naught, sigma 2 S naught, and so on. So I'm going to generate multiple answers for the same prompt. Not a single answer, but multiple answers. Okay. And then I'm going to compute the reward, total reward, from sigma 1 S naught from sigma 2 S naught. So this is given by, what is the total reward? This is summation SA in sigma R phi of SA. Right? That's how you compute the total reward. For every sigma 1, sigma 2, sigma 3, and so on, I compute the total reward. And then I define this A hat IT, which is the total reward Okay, now here is where I am not very sure about what their paper is trying to do. So I am going to do things according to how I understand what they are trying to write in the paper in math, but I could be totally wrong. So take it with a grain of salt. And just so you know, even from paper, you won't understand what exactly is it that they are trying to do. So I'm just going to write it up and uh, S naught minus mean. Not variance, standard deviation. Okay, and then they are saying minimize over theta, summation over I equals 1 to capital G, A hat, IT. And this algorithm is known as GRPO, Group Relative Policy Optimization. So total reward at time t is you are summing it up only until time t and not summing it up all the way to the end. So that's what I think, that this is what they are trying to do. They have written it in plain English, and so I'm not able to figure out what exactly is it that they are trying to do. But I think that this is what they are trying to do, which is take the total reward all the way up to time t, ignore the future reward, subtract the mean divided by the standard deviation of this total reward, and then you do the averaging here, maybe 1 over g, do the averaging here, and then replace this advantage function, which was estimated by a neural network. Instead of that, now you put this group relative advantage function here and try to solve the problem. So the good thing is now you don't have to keep track of another neural network of advantage function. You already have the reward function R phi, so you can compute this particular total reward. You can use the total reward up to time t in order to define this group relative advantage function, and then you can do the optimization. and get a better uh, model than what it was before. All you want to do is improve the model along certain dimensions, and so they were able to do it, and this actually caused a lot of uh, activity in the area of training of large language models, because everybody was using PPO, and they were able to come up with GRPO and improve the training performance significantly while using much lower computation. So they didn't have as many GPU, so they were able to come up with this algorithm, and they were able to improve the performance and beat all the US models at that particular point of time. So that is the GRPO algorithm, and I think, if I'm not mistaken, a lot of other companies have adopted this algorithm now for training or fine tuning neural network, okay, using human preferences. So that's roughly what I'm pretty much towards the end of my lecture, but that's what the three topics were. Inverse reinforcement learning, I have policy. I want to map it to a reward function. Then we have reinforcement learning with human feedback, which means I have preferences. I want to map it to a reward function. And then you have this alternative to PPO for training neural network, especially in this large language model settings where you have a huge parameter space, as a result of which you don't want to keep track of another advantage function, and therefore you use group relative advantage function to train the policy. GRPO algorithm, as far as I know, has not been investigated rigorously, and there are many downstream algorithms that have come out of GRPO algorithm as well, which I'm not talking about today. But I guess one open problem is to understand the convergence property of GRPO and whether it's converging to mu star, which is the optimal policy, or is it converging to something that's, I don't know, some policy, but it may not be optimal. But what sort of suboptimality gap do we have with respect to the truly optimal policy? So we don't know that. But things that are kind of unknown at this point of time, as far as I know, is whether this is actually computing the true reward function. So remember, the existence of reward function was proved in von Neumann and Morgenstern's book back in 1944. So that was the existence of a reward function. But whether this leads to a consistent reward function or not, if I have infinite data, can I would this reward function be the true reward function that is coming out of von Neumann Morgenstern utility theory? I think that's an open problem. In fact, I think that nobody has actually made the connection either between the utility theory studied in economics and the reinforcement learning with human feedback that people are studying in large language models. So there is a connection. Nobody has made that connection. Nobody has studied the consistency of this particular approach, and nobody has studied the convergence properties of GRPO algorithms. So these are all sort of open modern problems in reinforcement learning. So that brings me to the end of the class. My job is over. Now your job starts. So next week on Monday, Thursday, and then on the Tuesday of next week, next to next week, we'll have the class presentations. The class presentations will not be recorded. If you want to record your presentation, that's completely fine, but I'm not going to be recording it. It's up to you whether you want to record it or not. And people have signed up for the class, for the schedule, but the problem is nobody has given the title of the project and nobody has written down their email address. So please go back, write the title of your project and email address. So if anyone else has a question on your presentation, they can send you questions. And I have only 23 people who have signed up, but 25 people are registered for the course. So 2% who has not yet signed up, please do sign up. You don't want to miss out on the grades for this particular course project. So that's pretty much it. Thank you so much, and I'll see you guys next week on Tuesday. Have a great Thanksgiving break.